Hi, welcome back everybody. In the last video I went over how to visualize these logarithmic functions and how to visualize their graphs. In this video towards the end I'll go over some tricks on how to calculate these by mental math. Now you can do these quickly, and these tricks might be helpful for the MCAT. So let's look at these points. So you know that for exponential functions, 10 to the 0 is always equal to 1, and 10 to the 1 is always equal to 10. And so to be able to just do what we did here, and again convert it, we get log 1 is equal to 0, and log 10 is equal to 1. And so these are our 2 points on the y equals log x graph. So when x is 1, y is 0, when x is 10, y is 1 on this graph, right? So these are our points. So we can use this to be able to memorize and then estimate any log value. And actually, so if we know log of 1 is equal to 0, 1 is equal to 0, and log of 10 is equal to 1, we know that any log value in between is between 0 and 1. What is log of 0? Well, that's actually undefined. It's undefined. Because if you want 10 to the power of what is equal to 0, nothing to the power of anything. You can't take this to any to the power in no situation in which this would be equal to 0. So actually, if you noticed on the previous graph, there was a small mistake. So this should not be here. Obviously, this is an inverse of this, so you can see how this is approaching from negative infinity from the x from this side. But it should be asymptotically approaching this axis, right? It should not be touching here. There should be no y-intercept on this. There should be no as similar to how this doesn't touch the x-axis. This should not be touching the y-axis when it is flipped. So let's redraw how that graph really should look. It should be looking like. So excuse my poor drawing of this graph, but I encourage you to go look at it on Desmos, and you would see how this is an inverse of y equals 10 to the x. So y equals log x is an inverse of this exponential function y equals 10 to the x. And so we would have our point at 10, 1 here. So let's just say here is not to scale, but this is 10, right? And let's just say it's not to scale, and this is 10. And so that point is 10, 1 on the y equals log x graph. And so anyway, we have these points. And so now, now that we know this, we know that we can calculate any log value, because between log of 1 is equal to 0 and log 10 is equal to 1, we know that something in between there, that log of 3, for example, log of 3, will be between 0 and 1. And so the rate at which that increases, it's exponentially increasing what this y value is, right? Because we can see that y equals log x is sort of an exponential increase in it's the inverse of the exponential function, so it's like kind of an exponential increase when we're going there. So it's useful because you can, if you memorize the values between the log of 1 and log of 10 estimated values here, then you can basically be able to calculate any log value, which will be helpful for the MCAT. So log 3 being between 0 and 1, we know if we reverse this in exponential form, so 10 to the n is equal to 3, we know that that power is between 0 and 1. And so if we write out these things, we know we write out anything between log of 1 and 10, it will be between 0 and 1. And if we memorize these values between log 1 and 10, we can calculate a lot of different log functions, because we can make anything into a multiple of 10 and be able to calculate it. So for example, if we have log 10 of 1 is equal to 0, the same thing again, 10 to 0 is 1, log of 10 equals 1, 10 to 1 equals 10. So in between that, we have these values. So if we go a little bit increase, just think about if we go log of 1.25, in between 1 and 10, log of 1.25, we have a bit increase, we have 0.1. And so I actually wrote out all these values and wrote out estimated values that are easier to memorize. And if we memorize these values, you can be able to calculate any log function. So if you see this, it's actually log of 2 is 0.3, and then everything from log 3 to 3, 4, 5, and 6, it's a 0.2 increase of that number, so that's easier to memorize. So log of 3 is 0.5, log of 4 is 0.6, log of 5 is 0.7, log of 6 is 0.8, and then memorize these. Log of 7 is 0.85, log of 8 is 0.9, log of 9 is 0.96. And so if you memorize log of 2 is equal to 0.3, and log of 7, log of 8, and log of 9, and you know log of 1 and log of 10, you can be able to pretty much estimate any log value. And so this is, you can see the amount of increase to as we go from log 1 to log 10. And so you can see here we have a 0.3 increase, and then here we have a 0.2, here it's 0.1, here it's 0.1, about. Remember, these are all estimated values, they're not exact values, but the estimates are mostly pretty accurate, pretty close to what the real value is. But this is 0.05, right, and this is 0.05. About 0.05. And so from here to here, it's about 0.04. And so you can see it's decreasing in the rate at which it's increasing, right? So it's like a derivative. The rate it's increasing, but the rate at which it's increasing is decreasing, right? So so the log function is increasing. It's increasing like this, and then it's not increasing as fast anymore. So the rate at which it's increasing is decreasing. So that rate at which this function, remember, it's approaching an asymptote like this, right? And I mean, it's going off, it's increasing into infinity, but the rate at which here it's increasing faster than it is increasing here, because that slope, the tangent line, the derivative here is much steeper, and then here it's less so steep, so it's not increasing as fast anymore. So you can see that rate, you can see it right here, the rate at which it's increasing is decreasing. And so if you memorize these values, you can be able to calculate any log value, and it's really helpful. The Kaplan way, they show a trick that sometimes might be helpful if you forget these log values, but sometimes those values are a little bit less accurate. The Kaplan trick is if you have m times 10 to the negative n, then you would take negative log of m times 10 to the negative n is equal to n minus 1 that 10 minus m. And so that's the formula. If you forget, you can think of this as like a smiley face. These eyes are in the middle. You have your mouse ears, here are the eyes, and whiskers or something, cheeks. That's a little trick to remember that. So n minus 1 that 10 minus m, that's the formula of negative log of m times 10 to the negative n. So for example, if you have, we're taking 2 times 10 to the negative 1, for example, and you want to take the negative log of that. Negative log of 2 times 10 to the negative 1. So what is that? That is equal to m times 10 to the negative n. So this is m, this is your n. So n minus 1, negative 1, minus 1. Sorry, this is positive. You would take this, so this negative 1, this is your n is 1. So 1 minus 1 is equal to 0. And 10 minus m, 10 minus 2 is 8. So that's the estimation. That is less accurate because we can have it, if we have the values memorized, we can better understand what's going on and also be able to do it a little bit more quickly. So let's say if you have 2 times 10 to the negative 3 that you want to take. So let's say you're doing negative log of 2 times 10 to the negative 3 by the Kaplan method. So our n is 3, so this is equal to n minus 1, so 3 minus 1 is 2, 10 minus 2 is 8, so 0.8. So that's the estimated value by Kaplan. But if you do it via our estimated values, we can actually get a little bit more accurate answer. You know that via log rules, if you have log of a times b, it's equal to, you can turn that multiplication into addition as log of a plus b. So this is equal to negative log of 2 minus, because of that negative sign, or plus negative log of 10 to the negative 3, right? I mean, this is log base 10 too, but just want to write it out here. So you can see that negative log of 2 above, based on our memorized values here, our chart here, log of 2 is 0.3, so that's negative 0.3 plus, and then this is just equal to 3, because log 10, 10, log 10, what exponent do I have to get here? That's negative 3, but you have this negative sign here, so that cancels out, so it's a positive 3. So that value is 2.7, and this is much more an accurate value. I know it's a 0.1 difference, and it might not be a big deal, but this is a much more accurate way, an easier way, a quicker way to be able to do this really quickly. So let's just really quickly compare this to the Kaplan method and why this part of the Kaplan method is correct and this part is an estimation. So again, if you split this up, this is equal to negative log of 2 minus, remember you split this into a plus b, and then you have this minus sign, so minus log of 10 to the negative 3. And so you know that it's just negative 3, and that negative sign gets out, so that's plus equals 3 minus log 2. And so in the Kaplan method, you do this n minus 1 dot 10 minus m, you get 2, and then 10 minus 2, 0.8. And so this part is correct, so you have 3 minus this value. So every time you're getting this part of the answer is correct, negative log of 10 to the negative 3. That's a very correct answer. But when we come to log of 2, we're estimating that value. And so we know that because this is a minus sign, it'll always be less than 3. It'll always be a little bit less than 3 because it has to be negative log times 10 to the negative 3 is definitely for surely 3. And then you have minus log 2, right? You have this minus log 2. So this is your estimated value. It's always going to be a little bit less than 3. And so that's why this first part is always correct. And this part is the estimation. So you have 10 minus 2, and so they're estimating log 2 as being equal to 0.2. And so that's why you're minus log 2. They're estimating it by Kaplan. You're estimating log 2 as being 0.2. But if we look at our memorized values, we see that log of 2 is more closer to 0.3 in actuality. So they're actually, in the Kaplan method, they're saying log of 2 is 0.2, log of 3 is 0.3, log of 4 is 0.4, log of 5 is 0.6. And so you can see that it's more accurate in the lower log values, but this is a little bit less accurate because log of 8 is not 0.8, it's actually 0.9, log of 6 is not 0.6, it's 0.8. So here it's a little bit less accurate. And so if you are able to memorize these values, it'll help you in the long run because you're able to do it really much quicker, and you can do it, find a much more accurate way to be able to do this every single time. So let's do a quick example with OH concentration, and I'll show you that no matter if this is 2 or 200 or this is 3 or 300, you should be able to split it up and be able to calculate via this method with any number. So for example, let's say you have a OH hydroxide concentration of 300 times 10 to the negative 2 molar. So we want to find the pOH. What do we have to do? We have to take the negative log of this. So you can split this up into 3 times 10 to the 2 times 10 to the negative 2. And you can add these exponents. So 2 plus negative 2 is 0, and that is equal to 1. So this is just equal to 3 molar. So you would really just be taking the negative log of 3. And see, by Kaplan, you would kind of have to put, it's a little bit confusing, but if you had it memorized, you would just know that's about 0.5, right? About negative 0.5, right? Because you know log of 3 is 0.5. And so that's much quicker and really handy to be able to do any log calculation quickly. So if you have OH concentration of, now let's say 3,000 times 10 to the negative 2 molar, you can really think of this as, 3 times 10 to the 3 times 10 to the negative 2. And obviously you can just kind of move this 2 ways to the left as well, but just to write it out, this would be 3 times 10 to the 1. And so if you're taking the negative log of that, you can just do negative log of 3 times 10 to the 1, which is really just 30, but just to show it, you would have negative log of 10 to the 1, that's equal to log of 3, so then that would be 1 minus log of 3, which would equal to 0.5. And so that's a really quick way to be able to calculate it. So let's do one more. So if you have OH concentration of 3 times negative 10 to negative 2 molar, you could just do negative log of 3 times 10 to the negative 2, and that would equal negative log of 3 plus negative log of 10 to the negative 2. Again, that's just 2 minus log of 3, so equals 2 minus log of 3. So you could be able to do this really quickly. Either by the Kaplan method, you would just do, this would be 1.7 by the Kaplan method because n minus 1, 10 minus 3, so 1.7. But if you have this, you could also just do it really by mental math. You could just say, negative log of 10 to the negative 2, that's 2. Negative log of 3, that's minus log of 3, so 2 minus log of 3. And log of 3 is 0.5, so that's equal to 1.5. And by the Kaplan method, you would actually get 1.7 because log of 3 you're really estimating as 0.3 by Kaplan method. But by our estimated values, it's actually closer to if you estimate as 0.5. And so you can do this and really quickly, and you get your answer 1.5, a more accurate way to be able to do log calculations really fast. And if you have, no matter what, if this is 3,000, 300, you can split it up. So if you can split these values in between 1 and 10, you can really be able to calculate any log value. It might be tough to be able to calculate some bigger numbers, but for example, if you have a log of 25, right, that's the same thing as log of 5 squared, right? And you can just put this to the front. So 2 log 5, and log of 5 is 0.7, so that's equal to 2 times 7 over 10. And so you're able to really quickly get that as 1.4. And so that's a really quick way to be able to calculate these values. Or, of course, you can, if you have log of 5 times 5, that's equal to log of 5 plus log of 5. And because that's 0.7 plus 0.7, that's 1.4. And so you could be able to do this any calculation really quickly. Let's do another example for just to see. Let's say you have log of 2,500. Again, you would just split this up into log of 25 times 10 to the 2, right? And so you know that log of 25 now is 1.4 plus log of 10 to the 2 is 2, right? Because you know that exponent is 2, so that's 3.4. And so you can be able to really, really calculate anything. But for example, if you have something a little bit more tough, like log of 333, for example, to be able to split that up, that's log of 111 times 3. And so you could be able to calculate log of 3 plus log, you can be able to calculate log of 3, but calculating log of 111 might be a little bit tough. But you can just kind of estimate it. So you know that log of 100, if you do log of 10 to the 2, which is log of 100, what would that be equal to? That would be equal to 2, right? But if you take log of something like 1,000, what would that be equal to? 10 to the 3, that would be equal to 3. So you know this value is in between 2 and 3, right? So this is 0.5, and this is 0.5. And then this value would be somewhere in between 2 and 3. And so it's closer to 100 than it is close to 1,000, so you can estimate that as around equal to like 2.1 or something like that, or 2.05 or something like that, whatever, and you would get around 2.6, sorry, you get like 2.6. And so you can estimate really even these tough numbers, you can be able to split it up, and based on what you know, as long as you know your log 1 to 10, you can really split up anything and be able to split it up as a divisible number and be able to estimate anything. And you can estimate it based on what you know on these values and exponential increase. And in between log of 10 and 1,000, it's like an exponential increase based on the chart. So like, for example, log of log of what I showed here, log of 1 is 0. Between, if you know log of 1 and 2 and you want to find out something that's in between 0 and 0.3, know that like just very small increases, that's like just to get like kind of a sense here. Log of 1.25, it's 0.1. So if you're increasing, you think 0 bit 0.3, increasing by 0.1, you're only going up by 0.25 in the log scale to be able to go up by 0.1 in your y value. So, and even here log of 3 is not really log of 3.5, it's actually log of 3.16. I just wrote this out because it's a little bit easier to memorize, but it's really, really close, you see that. So even 3.16, between 3 and 3.16, you can be able to estimate any values in between. Let's say you want to estimate something in between 0.5 and 0.6, so you know that's in between log 3 and 4, and that's really helpful. That's enough to know to be able to do this trick, to be able to calculate any log value. And so I hope that was helpful. This chart is really helpful if you want to screenshot it and then memorize this values. It'll take a few minutes, just sit down and memorize these values, and it will really be helpful because you'll really be able to calculate any log function, and you can do it really quickly. Versus using the Kaplan method, you can do it quickly if you forget this method, but just know that the Kaplan method will be a little bit less accurate, and it's okay. For the multiple choice, you might be able to just do it really fast. So 3 minus 1, 2 10 minus 10 minus 2, 2.7, you can do it really fast. But if you have this memorized, it's really much easier because you know negative log of 10 to negative 3 is just like 3 minus log of 2. You know log of 2 is 0.3, so you would just do it much quicker, 2.7, versus in the Kaplan method you would get 2.8. So again, it's much quicker. Hope that was helpful.
Thanks for watching. Hope you have a great day.